Hello everyone, welcome to this video. In this video, we'll be looking at another question from IIT-JAM question paper Mathematical Statistics, and the subject is linear algebra. So here we are to solve this question. It states that they are asking the number of real roots for this polynomial. This polynomial is given to us. For this polynomial, how many real roots would be there? So this is the question, right? So let's see. This is a 2-mark question and the result is quite simple. You just have to know a simple result. So if you know this result, then you are through this question in a few seconds only. So the result is Descartes' rule of sign. So here this rule tell you that how many real positive roots are there and how many real negative roots are there for some given polynomial. So whenever we are seeing the real positive roots, we are to check we have to count the consecutive changes in sign of the given polynomial f of x. So whichever is that many changes in the sign of fx would give you the number of positive real roots for the given polynomial f of x, right? So this is the thing whenever you wanted to check for the positive real roots. Now whenever you wanted to check the negative real roots, what you have to do, you just have to replace x with minus x. So you just have to make this replacement, right? Once you make this replacement, what you again have to do, you have to count the consecutive changes in sign. Now of what? You have to calculate the changes in sign of f of minus of x. So that means you have, in your given polynomial, you have to replace the x with minus x and then see what are the changes. So the number of changes that you would count here would be equivalent to the number of negative real roots for the polynomial f of x. So this is the rule. And moreover, the complex roots, suppose these are p, these are q, then the degree of f of x, say the degree of f of x is equal to n. In that case, the number of complex roots that would be equal to So you can count these complex roots by just subtracting all the real roots from the degree of the polynomial. Why? Because these are these many roots you can find for any given real polynomial, right? So you could subtract all the real roots from the total number of roots, which is nothing but the degree of the polynomial. In that case, you would have the complex roots. Now let's move on to our question. In our question, we are to calculate the real roots, right? So in order to have the real roots, let me write down my polynomial. So we have this f of x as x to the power 11 minus 13x plus 5, right? So minus 13x plus 5. So now in this polynomial, the number of, actually we do not require positive and negative roots separately, but we want the total number of real roots. For that, we have to calculate positive real roots as well as negative real roots. So here the number of positive real roots would be, so you see we have a plus sign here, we have a minus sign here, and we have a plus sign over here. So that means we have a change in sign here in moving from this first term, and moreover we have a change in sign here. So the total change in sign are 2, so therefore we have 2 as the number of positive real roots. Next we wanted to see, we have to replace x with minus x, right? So in that case, we would have f of minus x as it is minus x to the power 11 minus 13 minus x plus 5. So you could solve this. Minus 1 to the power 11 is minus only, so minus x to the power 11, and it would become plus 13x and plus 5. Now we have to check the signs of this polynomial f of minus x. So here you see a negative sign, here you have a positive sign, and here you have a positive sign. So you see we only have one change in sign in moving from this term to this term. So therefore that means the number of negative real roots would be equal to 1 in this case, right? So if that is so, if we have 2 as positive roots and 1 as negative real root, so that means the total number of real roots there would be equal to 3, right? So this is your final solution. So I hope you understood this question well. That is it for this video. Thank you for watching.